Okay, with that, I think we can kick it off. We have Petar joining in today. I don't think he needs a lot of introduction. He's a staff research scientist at DeepMind. He's famous as the first author of the Graph Attention Network paper, which I think at this point has almost 19,000 citations, which makes Petar one of the world-renowned experts on graph ML and I guess geometric ML since recently. And he's going to join us. He's joining us today to discuss his latest work, TacticAI. And with that, I'm gonna hand it over to you, Petar, and you can kick it off.
Hey guys, I want to give a huge shout out to Hyperstack folks who have generously sponsored my compute over the past month or so. Basically, I got 16 H100s, which is 2 8 GPU nodes, and the performance has been amazing. Basically, 2x the speed up compared to my A100 nodes. So I want to quickly show you how you can get started yourself. It takes basically 3 steps only. You go to the environments here, you create a new environment, you give it a name, you pick between Canada and Norway. That's the first step. The second step, you go to SSH keys here, you create a new pair, you pick environment you just created, you give it a name, you paste your public SSH key. That's it. And finally, go to virtual machines, deploy new machine, give it a name again, select environment. Let's select Canada here because they have more compute there. Then you select the hardware you want, like for example H100s, you select the images, you select the SSH key you just created, and hit deploy. That's it, literally a couple of minutes to get started. It was really easy for me to just basically create these 2 nodes I just mentioned and get started running LLM trainings. So the documentation is super cool. I could actually solve all of my problems just by looking at their docs. They additionally have a Slack channel where they were super helpful, so I can't recommend them enough. Honestly, the thing they kind of focus on is basically because a lot of these GPU providers focus on big enterprises, so oftentimes you can't get on-demand H100s, whereas NextGen focuses particularly on that. You can get top-of-the-line hardware on demand, even if you're an individual or like a smaller team or whatnot. They also focus on bigger companies, but that's kind of their edge here. So without further ado, guys, let's go back to the talk. I do suggest you check them out, and let's continue.
Thanks so much, Aleksa, for having me on your Discord again, and thank you all for coming along for today's presentation. I see a lot of names that I know or have collaborated with or talked to before, so it's great to see all of you again. And for those of you who maybe haven't had a chance to listen to me speak before, I hope you'll have a good time. I think some people have joined in after I said this, so I'll just repeat it again. Please feel free to ask questions during the talk, and I will try to take them. I'll try to regularly check what's inside the chat box or if anybody has their hand raised. I can stick around for like 1 hour and a half from now, basically, so there should be enough time to cover everything.
That's awesome. Just briefly on my side, so if you want to ask a question, please raise a hand, and then I'll be moderating. That's easier than Petar taking every single question. And yeah, with respect to time, I think I have roughly 1 hour. So let's try and get it inside of 1 hour. But for the questions, we can also do it on Discord later as well.
Yeah,
awesome.
That also works. So, right. So as already mentioned by Aleksa, hi everyone. My name is Petar Veličković. I'm a staff researcher at Google DeepMind and affiliate lecturer at Cambridge. And what I'm going to talk to you about today is, well, I would say arguably one of the most fun things I got to work on in my professional life so far. And it's something that I'm very, very proud of and something I really enjoyed working on. And it also draws on some of the things that are well within the things that I'm good at and the things that are part of my expertise and parts of machine learning I'm very passionate about. So I hope that all in all, it's going to be a really fun conversation and a very enthusiastic talk. As you can see from the title, we're going to be talking about AI assistance for football tactics. And I feel like maybe before we dive into the specifics of what was done, it might make sense to just start from, what do we mean when we say AI for football? And this is actually a picture of myself taken at Liverpool's AXA Training Center. So maybe let's start from motivation. So a lot of you, I hope, have seen a football game in the past and are sort of familiar with the kinds of things that happen inside a football game. As you might imagine, an actual football coach is tasked with looking at specific tactical plays that took place in previous games and based on them detecting some specific patterns or details that we might want to focus on when we train a team for a new game, and then, you know, coming up with new tactical strategies in which we will tackle the next teams head on, right? But when you think about it, this is really something that relies a lot on pattern detection, pattern matching, and making decisions from data, sometimes really complicated, noisy real-world data. And that is something that, as you probably know, artificial intelligence can be particularly well-positioned to answer. And I would actually say an AI system that can detect patterns from football data might be an AI that learns from a very rich collection of data points as well. So you might imagine, you know, player tracking data, video data, audio data from commentary, or even textual data from transcripts. There's a lot of potential for different data sources you might want to take on board and integrate to try to detect tactical patterns, right? Lots of treasure troves of data for AI here. And you could imagine AI doing some of the detection work that a coach might need to do. So maybe let's just hammer that point home on why we believe football would benefit from an AI-style intervention and AI assistance. First of all, football is a really dynamic and really challenging game to analyze, and the outcomes that happen, like who takes a shot, whether there'll be a goal or anything like this, often depends on many very latent factors like human psychology, fatigue, how tired the players are, what's the weather outside, things like that. And how these factors influence the outcomes is very complex, right? And even for someone who's like a top-tier football expert, it's really tricky. Like, they're paid to detect these patterns, among other things, but it's really tricky to detect all of them and then also track them across 22 players at the same time. It's not easy. And in my opinion, AI is a really natural assistant in this endeavor, and it can really help us detect things automatically that might take us much longer to detect. And once we see them, then we can hopefully focus on the more creative parts of coaching, which is, once we see them, what do we do about them, right? And I would say it's not just that football could benefit from an AI system implemented inside it. I would actually also argue that it's the other way around. I think artificial intelligence as a whole can benefit a lot from looking at things like football. And why is that the case? First of all, let's look at what happens inside the game of football and what kind of data is available to us from a game of football. So first of all, there are lots of interactions happening between players on the pitch. There's a clear, like, multi-agent real-world system of humans in there. It's often interpretable, like post hoc, you can make sense of what has happened, and very, very multimodal. There are many different sources of data you might gain access to, and all of these data come from the real world. And this is a great test bed for the development of AI systems. And also, basically, it's also a system that is generally safe to analyze. Like, you can make decisions inside a football game. Worst case scenario, if you make a mistake, your team might concede a goal or something like this, but nobody will get hurt or anything like that, right? Whereas in some other areas where AI is making an impact, like medicine, for example, if you make a bad decision and that decision gets followed, the consequences might be much worse, right? So football allows us to study a really complicated, challenging, real-world human setting with multiple agents in a way that is generally safe for decision making. And generally, because data comes from multiple disciplines, it's a great avenue to combine any expertise you might have in computer vision with any expertise you might have in game theory, and also any statistical or machine learning experience you have. And also, there's a reasonably clear metric to measure how much you've made progress if you deploy a system like this in the real world. You can track whether or not your team is on course to win a season or anything like this based on decisions you're making. You often cannot influence completely any one particular situation. There's always a bit of human factor and noise involved there. However, integrated over a season, if you're better tactically, you're going to score better on average and you're going to perform better, right? So there is a way to track how well your decisions are faring in the real world. So all of these things were very much top of mind for us at Google DeepMind when we started off the collaboration with Liverpool. And this is something that's taken a course over many, many years. So this is not something that only just came out now. Google DeepMind has been working with Liverpool for many, many years. And before we dive into what's happening with the paper today, I'm going to tell you a little bit about what has happened before, and also leave you a lot of interesting pointers, hopefully, if you want to learn more and maybe have some layman shareable material. If you want to tell your friends all about how AI might be impacting football, there are lots of really cool resources you can share with them. So our collaboration actually kicked off around 2019, so it's been a long time in machine learning terms. And there's been lots of serendipitous connections that kicked it off. In part, it also helped that Demis, our CEO, is a really big fan and supporter of Liverpool. This helped make these connections easier. And also the fact that Liverpool has a really, really strong data team with people who generally have STEM PhDs in areas like physics and astrophysics. So these people very much spoke the same language we did. And it was much easier to help them because the club was already very data-driven to begin with. So they didn't have particular deep learning experience, but they were very much open-minded to learn from it. So the first work that we have done together actually came out, and I was not part of the project at this time. This was 2021. The paper called Game Plan, which is more of a motivating paper. So it tries to outline why should AI be used in assisting football tactics. It had a few motivating examples like penalty kicks and things like that. But generally, it's more of a survey paper outlining why this is a good idea, right? And as a basis from this paper, we started then to get more of the community interested. And throughout 2021, we have done several engagements resulting in artifacts that both researchers and sports people might find interesting to peruse to learn more. So at IJCAI, which is one of the top AI conferences, we organized a workshop on AI for sports. This was 2021. Together with a few other co-authors, Carl Toils, who was one of the leaders of the sports AI effort from GDM's side. He wrote a book on AI for sports, which is publicly available. You can take a look at that as well. But the resource I would most wholeheartedly recommend, if you want to share this with someone and just have them learn more about the synergies of AI in football, is we also did an entire episode for DeepMind, the podcast, hosted by Hannah Fry. So this was episode 7 of season 2. DeepMind, the podcast, is, by the way, a fantastic resource because it's a great way to get introduced with all the various things AI can do for someone who is a layman. And this particular episode focuses almost entirely on sports. And it's just really brilliantly presented. I enjoyed listening to it, even though like I'm already familiar with the technical aspects of everything that's going on. So I would highly recommend checking that out, that episode and the entire podcast, if you want to know more about how DeepMind applies artificial intelligence solutions to solve real-world problems. And then, obviously, we had that foundation. We had the momentum of the community. And then it was time to try to write something up that concretely demonstrates a prototype of how an artificial intelligence system could be used to analyze a specific task inside football tactics that a coach might be interested in. And this led us, once again, I was not part of the project at this time. I only joined in late 2022. But basically, this is the Graph-Imputer paper that was published at Scientific Reports. And I feel like I'm not going to talk a lot about Graph-Imputer today. There's a pointer to the paper if you want to read more. But I will show you one video which very clearly explains how Graph-Imputer works. So the point of the Graph-Imputer is predicting off-camera behavior of players. So as you might imagine, we, like a club, might be interested to recruit certain players to join their team. And scouts are charged with discovering these talented players, sometimes in pretty remote leagues. Now, if those remote leagues do not offer access to tracking data, you cannot gain access to these nice visualizations showing you where each player has moved throughout the entire game. And typically what you have to do in these situations is you have to send a scout, sometimes to a very remote part of the world, to analyze this game and figure out who are the most impactful players to look at. However, this is a very costly thing and obviously doesn't scale. You only have so many scouts. So one other thing you could try to do is actually rely on what the camera can see, because for a lot of these games, there will be YouTube videos and things like that that you can gain access to, right? So if you had a good system that would be able to tell you roughly what the players outside of the view of the camera are doing, you would be able to then reconstruct pictures like these, and then rather than sending a scout to watch a game remotely, they can just watch a generation from the graph computer and use that to drive their decision making. And we've demonstrated in the graph computer paper that you can actually do this with a reasonable level of mean squared error, such that hopefully this could be something that might make it into an actual scout-facing system. Yes, Alex, I have a question.
Petar, can you help me understand how does one use this as an end user, like to gain some insight about the game, because it's very abstracted.
Right.
And
I mean,
yeah, how do you parse this one? Or is it meant for humans, I guess, or is it an intermediate step for something else?
No, this is mainly meant for human scouts. So, for example, the bright area is the part that the camera can see, and you basically, like, you can see for those players in the camera's view, you know exactly where they are, so that's great. But as you can see, depending on what the cameraman chooses to focus on, there are many things outside of the view of the camera that might be really important tactically, right? So you might want to be able to predict where those players are off camera, and you don't see this just by watching the video. So the idea is that this can help you make a good best chance guess of where those players are, conditioned on everything that the camera was able to see. And the idea is that then basically, yes, exactly. In the final version, the scout would only see the prediction of the model rather than the target. And this is substantially cheaper than sending the scout to watch the game live if it's somewhere in a remote part of the world. So this
Got it. And I would assume that there are some like labels with actual player names on the graph when
yeah,
they're looking at it, or
you can put any features you want into these nodes, depending on what you know about the players. I don't know the specifics of which features went into this particular work, but the general idea is in this case, they have ground truth full tracking data from the Premier League, and they have basically looked at cameras, like they've simulated certain players not being in the field of view and trying to see how well can the system predict what those players are doing when they're off camera, right?
Nice.
That's generally the idea. You can read more in the paper. It's published in Scientific Reports in 2022. You can find out more about it there. But then this leads us to 2023, where we have developed TacticAI, which really is a system that tries to go one step beyond that. So Graph Computer really is just a prototype showing you that there is something where you can essentially try to deploy this, and it's a task that might be of use to a football club. But we've just shown mean squared error is relatively low, but it doesn't tell you much about how useful a human would find it. So with TacticAI, we actually set out to make something useful. And we have been successful, along with my collaborators, Joe Wong and Daniel Hennes and many others, and also William Spearman from Liverpool. We have been able to write up a paper that was published in Nature Communications a few weeks back, which we're very excited about. And one thing that's important is that it's able to answer many different kinds of questions about the football game. And I would actually even go as far as to say is it is a full AI system. So not just a prototype, it's a full AI system that's capable of giving useful tactical suggestions to coaches. Now, of course, this is a very loaded statement, and it sounds very bombastic. I am promising you this is not going to be just a hype statement, and I'm going to leave it at that. I will hopefully give you concrete evidence to why we believe it's both practical and useful. Okay, like we're going to go through both of these arguments, but this is my claim, and this is what we claimed in Nature Communications, our paper as well. All right, so let's first focus on the word useful, because what do we mean by useful, right? It's not just enough that a machine learning system gives you a good prediction accuracy, right? You also need to have it in a way that a human coach can actually do something useful with it, right? And if you think about it, if you've ever seen a football game, you'll know that football is highly dynamic, hard to influence. And while you could make a model that models open play like Graph Computer is, right? If you want to make a decision on the fly based on what a system like this tells you, it's really hard. There's 22 players on the pitch. You might see some immediate opportunity to improve the tactics, but imagine a coach shouting at the players every single, 10 seconds or 10 minutes or something like this. You are bound to confuse the players more than anything else, right? They have lots of very well-practiced things that they do ahead of a match that they should stick to, ideally. And open play kind of, implementations are tricky. Fortunately for us, there exist parts of the football game known as set pieces, like this corner taken by Liverpool that you can see here, where the game is effectively frozen. And this is very useful for us because some of these very frozen moments in the game also allow us immediate goal scoring opportunities. So tactically, it's something we might really want to analyze, and something where human coaches might be able to make a more immediate intervention, right? So for those of you who have seen Moneyball, and if you haven't, I highly recommend you check out Moneyball. It's a really fun movie to watch, and it shows you a bit about how even simple statistical analysis can make a big difference in the game of sports. It worked so well, it focused on the game of baseball. And in baseball, every single step is a set piece, right? So if you've seen a game of baseball, you'll know that all the time the game is frozen. You're really just changing where different players are positioned and stuff like that, right? So in the case, we're basically looking at how can we apply the Moneyball idea, but apply it in the context of football, where most of the play is open. We need to make sure that we're looking at things where the play is not open for our suggestions to be meaningfully useful. And as you might know, in football, we have access to 4 different types of set pieces: penalties, throw-ins, free kicks, and corner kicks. Penalties, as you might know, are really, really impactful and offer you an immediate goal-scoring opportunity, so much so that in the original game plan paper, we already study penalties, right? However, you cannot just make a penalty kick analysis system and say, I've solved football, because penalties don't really happen that often, right? You need some very specific circumstances to happen before you'll get a chance to do a penalty. And as might have been suggested by that nice Liverpool corner kick you saw previously, we have specifically focused on corners as an ideal candidate for such a useful tactical suggestion system, because corner kicks are frequent. They occur at least about 10 times in each game. They are rigid. They always happen in the same place, meaning you don't have to model for different starting positions or pray for a different starting position. Unlike free kicks, for example, where they can be quite dangerous and frequent, but you need someone to foul you in the right place for a free kick to actually be immediately dangerous, right? And also, corners always allow for immediate goal-scoring opportunities, as you've seen in that one particular example. And so much so, this was one of the main surprising things I've discovered in my discussions, in our discussions with Liverpool Football Club. They're so much so important and rigid and frequent that strategies for corners are usually decided upfront well before a game ever takes place, because you really don't want any confusion. You want the players to be absolutely prepared for what is about to be executed in that particular point in time. So accordingly, if we want to make our predictions useful, because that's one of the important points we're trying to have in our system, we don't just want to have a impressive machine learning system. We want to make it actually useful. We make it a corner kick analysis system. I hope that this argumentation makes it clear why this is the case. And it was actually Liverpool who suggested us to do this. So we started off modeling open play, and it was actually folks from the Liverpool data team saying, this is really impressive, but you guys should really focus on corners. That is where the money is. That is where you can actually do something immediately useful. Okay. Now, hopefully this explains why the setup of corners is a good idea. Now let's talk a little bit about how we can actually model them. So what's inside our architecture? As you hopefully know, if you've seen some games of football before, you know that outcomes depend often on very complicated synergies between players. Some players might work really well together. Some attacker and defender might be particularly well or poorly suited to each other, depending on which side you're on. And therefore, a lot of what happens will depend on the relations and synergies between players. And we chose to model these using graphs because we believe that it is a more complicated kind of situation to try to look at things, to explicitly model the interactions between the players when you're making predictions. And this is actually part of what drew me into the project, because as some of you might know, I have a long history of trying to put graphs into places, and often with a decent level of success. So here are just a handful of examples. Hopefully some of you use Google Maps in your day-to-day to help you get where you need to go. The travel time estimate, which Google Maps gives you here, 44 minutes in this particular case in the Bay Area. Basically, sorry, this one is Seattle, actually. The travel time estimate is served currently in production everywhere in Google Maps with a graph neural network model that we have co-developed together with Google Maps. So I was part of a team that took this system, analyzed the actual graph structure of the road network, and produced a solution that was much better than the previous Google production baseline in terms of especially rare events like impending rush hours and things like that. I've also collaborated with mathematicians on analyzing complicated mathematical objects using graph nets, and this led to our paper that was published on the cover of Nature in 2021, as well as several follow-up mathematical papers, which showed how the patterns we detected were really, really helpful for the mathematicians that worked with us. So I think I have a decent amount of history of taking these structures and applying them to good use, both industrially and scientifically. So it was time to apply the same concepts to football. And you often see graphics like these, like the one you see in the top right corner. When we analyze how a club behaves in a particular setting, you might explicitly model, for example, how often different players will pass to each other and things like that, right? So in our effort, we explicitly model the relationships between players through graphs. Now, how does this work? I want to kind of bring this closer to you because I'm going to be showing a lot of pictures of the football field, and I want you to kind of have a clear image in your mind as to how those pictures map to actual inputs and outputs for our models, right? So here is a simplified corner kick situation, deliberately only with 6 players to avoid cluttering the image too much. So there's 6 players. What do we do with them? Each one of those players is a node in a graph. And for each one of them, we will have some feature vector, xi for node I, and those will tell you the features of those particular players, right? And we're further going to interconnect them in this graph structure. You might notice the graph structure is fully connected. That's on purpose, because in football, it's always a rigid setting, always 22 players, and you never know which synergies are going to be important. Human priors might not be fully accurate. So we're just going to let the GraphNet figure out by itself which connections are most important. But we will obviously give some features in the edges. You might see edges are colored differently. So we might give you, say, a feature of 0, 1, depending on whether the 2 players are in the same team or not, or something like this. And once we have a graph structure like this, then we can apply a graph neural network on it, which operates in the so-called message passing regime. And the way it works is basically you will update the features of each player from this input space X to some high-dimensional latent space H by taking into account features of all of the immediate neighbors of those players, in this case, all of their players. And this is then iterated for a few layers, stack more layers as usual in deep learning. And then based on these H vectors, you can make predictions about various things you care about in the football game. So this is how I want you to imagine what the model is actually doing under the hood. But I'll always show you pictures like the one on the left because it's easier to visualize corner situations using pictures. Yes, Aleksa?
Quick question on the features. If you're going to cover this later, then you don't have to answer now. But like, can you tell us a bit more about what goes into the features?
Yeah.
What's learnable? What do you like hard code inside of it?
Perfect. That's my next slide. So that's a great preemption. So here you go. This is a list of features and possible prediction targets. So specifically, what you might want to put in your node features are the player positions, so the X, Y coordinates on the pitch, their velocities at the moment when the ball is kicked. That's usually what we feed into the model, the moment when the corner is taken. There are different physical features. We specifically look at heights and weights because they're a very simple rudimentary feature which might tell you something about the player's physical ability. As we said, for edges, we might have a feature telling you are they teammates or opponents. And for graphs, because this might surprise you, but not every football pitch has exactly the same shape. So you track exactly where are the home and away goalposts for this particular pitch. And also maybe you can track things like time of day, weather, current score, and so on. And then you can predict various things as predictive modeling in different parts of this graph. So you can predict whether there will be a shot. This will be a whole graph classification because it relates to the entire situation. You can predict which player will receive the ball. That's the receiver prediction task, node classification. Or predict positions and velocities of players in the future. That would be node regression, right? So you can imagine you can do all of those different things in the graph structure. I should stress, by the way, that these are really simplistic features, and they're really the kinds of things that all clubs in the Premier League would typically have access to. So they have a data provider that will give them these features. There are tracking sensors on the players' jerseys that track where they are over time, and you can use that to track information. I should stress that every club has its own way of gathering data. Many of the top-tier elite clubs are very data-driven nowadays, so they will have a lot of specialized features about the player's psychology, about their form, about how they analyze different clubs' players. So you can imagine TacticAI, the way we presented it, as just showing how far you can get with the simplest features possible. But then you can imagine every club might be able to train their own systems using their own collections of features, which then bake in their own philosophy about what's important about a player, right? So this is just a blueprint saying what's possible, but there's nothing about this setup that's specific to corners or even specific to football. I saw there were a few questions in the chat about could this be applied to basketball and so on. The answer is absolutely. If it's a team sport and you want to model pairwise relations between players, there's nothing stopping you from using the core TacticAI model, just strapping in your own features, your own players, and your own data, right? But the ideas are very much the same. Okay, now there's a big challenge here. Like, we are not training a large language model. We are training a graph machine learning model on gold standard football data that actually happened. And clubs don't play that many games every season. That's not trillions or billions of games, right? You typically play about 100 games every single season, right? And we wanted to see how far you could go with this high quality data. Yes, synthetic data is also an option, but it is questionable how much will synthetic data teach you about what clubs actually do on the field, right? So there is a big question mark there, right? So what we can do with limited gold standard data? Well, this is where geometric deep learning comes into play, because we understand that we don't have enough data and we won't have enough gold standard data to train a really fully potent system of this scale. That being said, there are lots of interesting symmetries about the football pitch we can exploit to effectively reduce the amount of examples we need to meaningfully learn something at high scales, right? And this was one other place where it really was a great thing that, as I said, Liverpool data team folks have PhDs in physics and astrophysics. They understand symmetries really, really well, and they were able to tell us what the symmetries of the football pitch were and how to exploit them in equivariant models, maybe even better than we could explain it ourselves. So this was a really great aspect of our collaboration. So what this means is, oh yes, Aleksa, you have a question?
Any interesting symmetry you observed that you were surprised by?
So no, specifically here we baked in symmetries that they recommended us to use. We didn't observe anything else additionally, but there are more symmetries that you could exploit. Once again, just like we use rudimentary features, we use a rudimentary symmetry just to show how far you can get with it. But you could imagine building a TacticAI style model with different kinds of symmetries as well. We discussed a fair few of them, but we only used one in this paper.
Got it. Can you give me an example? What would be a symmetry here in a football game?
I am literally about to explain it. So
okay,
you're good at preempting myself.
I'm preempting you.
Sure. Yeah. So here's one corner kick situation, this time with all 22 players on the pitch. And actually now, like, once again, keep in the back of your minds, when I show you this, I'm actually representing a graph of those 22 players with the right features and stuff like that, but it's easier for us to look at it as a picture. So one symmetry we explored with our collaborators at Liverpool is essentially a D2 symmetry. So D2 is the dihedral group of horizontal and vertical reflections. And effectively what this means is that we are assuming that if you take a corner in a completely vertically or horizontally flipped situation, so on the different side of the pitch or on the opposite corner, that it is more or less tactically the same situation. Now, we always get this question when I present this. Of course, there is a minor effect on player footedness and things like that. So not everybody is prepared to take the corner from exactly all possible positions. But that being said, in modern football, players are so well trained to cope with these variations that what we got told from the folks at Liverpool is that for all intents and purposes, you can consider this to be a proper symmetry, even though it's approximate. And you can look at statistics from the Premier League, as in how many opportunities were scored from this corner versus that corner, and you can see it's almost exactly symmetric, these statistics. So teams are well prepared for handling reflected situations, if that makes sense. So what we do in terms of our architecture then is and this is different from data augmentation, right? This is an equivariant architecture. We are mathematically forcing our model to give us exactly the same answer in these 4 situations, right? And we also do data augmentation, but actually this helps a lot more than data augmentation does for our downstream performance. So we have these 4 different horizontal and vertical flips that you can apply to the pitch. Hopefully you can see the differences. And what we do is then we feed these 4 into TacticAI as different views. And those views are now allowed to interact with each other in certain special ways that preserve the symmetry. And every single blue line you see internally to TacticAI is like a graph neural network layer that operates over the concatenated features of those 2 particular views, right? So it's almost like a graph of different situations that you have in there. And then all of them are aggregated together in a way that preserves symmetry so that then you can predict the following about the situation. The first thing you can predict is something like receivers. So who will make first contact with the ball? This is a task that coaches very much like to know about. Second one, as you might expect, shot prediction. So will a shot be taken or not? You can predict this kind of thing, obviously very important. And lastly, which I'm personally most excited about, is how can we change the positions of the players to increase or decrease the probability of something like taking a shot? This is great because if done properly, it can give you immediate tactical suggestions. And this is what we're all about in our effort, right? So this is what the overarching architecture looks like. Hopefully it makes sense. And a lot of these are node level or graph level tasks. So you can hopefully see how we can do backprop from some of these without a lot of problems. To answer the question that was just asked by Kartik, we explicitly do not include the ball in the data. Because if we tell you which way the ball is going, that removes a lot of the confusion from the model and like immediately tells you what's about to happen more or less in terms of receivers or area of the receivers. So we deliberately want to see how good is the model at predicting stuff just based on the tactical positioning, because there's always variation on how good the kicker is at kicking the ball also, right? You don't want necessarily your model to be dependent on this. It can overfit to it very easily. So putting all of this together, we have this guided generation system that I told you about before, the generative model that predicts positions of players in tactical response. So let me demonstrate to you what the model is capable of doing on this particular situation. So here is a corner kick where a shot has actually happened. And we highlight these 4 different attackers, 1, 2, 3, 4, because they're going to be important for the analysis I'm going to show you in a second, right? So in this case, the red team was able to take a shot. Now, what TacticAI is capable of doing is predicting adjustments to the defensive players' positions and velocities, which are minor, not too big. Hopefully, you can see in the highlighted regions, some of the blue players have changed their positions. And in a way that actually reduces the predicted shot probability significantly, okay? And I should stress that these predictions don't just extend to shot probability, but also to the receiver prediction. So when we made this particular change that I'm showing you here, the receiver predictor's logics changed in this particular way. So you can see the probability that attacker 1 receives the ball has shot up, and the probability that attackers 2, 3, and 4 receive the ball have went down. So what this means is that the model has concluded that now this is tactically harder for the red team to convert. So it might actually make more sense to pass it to an attacker that's far away and poses less of a danger, right? So it's not just in the immediate shot outcome, it's also in some other predictions that our system puts. Now you might be wondering, hey, but this is a kind of chicken and egg problem where our system predicts the shot probabilities as well as the adjustments. Don't worry, I will address this in a second. This impression is not lost on me, okay? So actually, I'll start by, because it's a machine learning paper, I have to give you some quantitative numbers in terms of how good the system is on test data, but I'll soon tell you to forget all about them, actually. So we don't predict goal events directly because they're super, super rare in comparison to shot events, just to have a more balanced data set. And actually, shots are usually more indicative of what might happen. Goals depend on other things. Aleksa, did you have a question?
There are a couple of questions in the chat. Luke is asking how precise are player positioning suggestions? Is it half a meter? What's the resolution?
I would say, yeah, I can't say for sure, unfortunately. We do have plots on this in the supplementary which say like how big are the adjustments generally, but you can expect like, yeah, half a meter, a meter usually. It's more about the orientation and velocity that tell a lot more to the coach, to be honest, than the position itself. But yeah, it's useful to know. They're generally minor adjustments. So first, how good is the model at predicting receivers? And we look at top 3 accuracy mainly because predicting a receiver is tricky business. And often when you kick the ball into the box, there's many possible people who might jump at the opportunity, right? So I'm very happy that our system gets about 78.2% top 3 accuracy on predicting receivers. You'll see later on, humans are not much better than this, by the way. Humans are roughly the same level of performance. So this is a good start. So the model is decent at predicting in the test set of held out corners who's going to receive the ball. Predicting shots is much harder than predicting receivers, and actually our F1 score, to make into account the class imbalance, is actually quite weak. It's about 0.64, right? So it's not that good, but we will see soon that it's less about whether or not a shot will happen, more about probabilities and which event gives you a higher or lower probability. So I wouldn't worry too much about the F1 score here, but just in case you're wondering about the raw number, on a test set, we get about 6.64. I cannot tell you exactly, Rafael, the shot-non-shot ratio. Please check the paper. It's all in there. I don't have it on the top of my head. Yeah, but it's a relatively kind of imbalanced data set. Maybe about 10% of the corners result in shots. And we wanted to see just quantitatively do our... can someone link the paper, by the way? Because I'm just focused on the talk right now.
Yeah, ignore the comments, by the way. I'll just cherry pick the ones that matter.
So the guided generation, as I said, our adjustments can influence the shot predictor. So we can check if we take a corner where a shot has actually happened. If we adjust our defending team, does this saliently reduce the shot probability? It does. It reduces it with a very low p-value. So this is pretty good. And similarly, you can take a situation where a shot did not happen and move the attacking players. Once again, this with a very low p-value results in an increase of shot probability. You might be wondering why are the variances so big? It's just because it's integrated over many different situations where probabilities are different. But pairwise, considering the original situation and adjustment, the probability goes up or down. So that's why the p-value is very, very low. Okay. And also, it's important, right, because you can easily optimize a shot probability by just having a near offside situation where all the defenders are very stupidly positioned. So we wanted to make sure that the generations are actually plausible. And we looked at, can a simple MLP classifier tell apart real corners from TacticAI generated ones? It was a near chance level F1 score. So this is good news. But I should stress, you should now forget about all these numbers. It was really important for me to tell you about them because it's a machine learning paper and you might care about performance on a test set. But remember, we care about making corner kick systems useful, right? So while quantitative metrics are useful for like just general evaluation of systems, they're never the clearest indication of how humans will make advantage of these things, right? And you see similar effects with language models, right? Like you might get really good performance in a benchmark, but then a human tries to use it and it doesn't actually result in effect, right? So benchmarks are not always, resulting in what will be downstream behavior. And in the context of football, the things we're predicting in the benchmark passes or shots, it depends on many factors our model cannot see. So maybe you cannot expect it to be super accurate anyway. So to truly evaluate how useful is the system, we wanted to talk to humans and we wanted to talk to top-tier humans. Luckily, our collaboration with LFC was really helpful there. We managed to source 5 expert raters that deal with this kind of data and decisions based on it all the time. So we have people like video analysts, coaching assistants, data scientists. We even had a goalkeeper coach take part in the study. So it was a very, very good collection of top quality experts to help us analyze these things. And we really put them through a lot. We showed them 300 different corner kicks, both real and AI generated, to gauge various properties that we cared about in our system. And everything you see from now on are going to be results derived from those human case studies. So these are really the results you should care about, the vibes results, right? So first, let's validate this claim about about whether or not this system actually produces corners that are indistinguishable from real corners, right? And once again, we assigned a situation where basically the humans could say either real or generated in a blind study. And we looked at the distribution of scores assigned to real and generated. And basically, as you can see, those two distributions are indistinguishable. And they're both biased towards realism. So humans say both real and generated situations are generally real, which is good. It's a good place to start, right? And also receiver prediction. I told you a hint that this 78% accuracy that TacticAI achieved on its test set isn't that different from human accuracy. And actually, the human accuracy top 3 is about 79%. We asked them, who is the receiver of this corner? And what's really cool, not only is it comparable with TacticAI, but also on generated situations where obviously we don't have ground truth labels, but we have to use TacticAI's predictor to predict who the receiver is going to be. The accuracy is still around 79%. So basically, the human predictions are matched both by TacticAI out of the field and on real situations, which is good news because it means that when you pitch TacticAI a new situation, you can sort of expect that its predictions will align with human intuitions reasonably well, right? And maybe the big takeaway from this is that experts cannot distinguish these TacticAI adjustments from real corners, and experts predict them, the receivers, equally well as TacticAI. Aleksa, you had a question?
This is impressive. Can you just go back to the last slide?
Sure.
So the top chart, help me parse it. Like I understand the bottommost one. So basically, you're asking who's going to receive this ball given the direction and velocity or some information like that you give to like both human and your algorithm. But for the top one, what does it mean adjustment? What's adjustment there?
No, this is really just the top one. You are asking, is this real or generated? So they say real or generated, and that's it, right?
And you're given what, like a vector of the ball from the corner, or
you have a picture of the positions and velocities, right? And you ask, is this a real corner that happened in the Premier League or not, right?
Got it. That's a very hard problem, though. If you're given a static image and then just like ascribing velocities or whatnot, that sounds like a very hard problem for humans. If I were to see a video, then that would be much easier. But like,
but we're not generating video, right? So there would be no way for us to show them this, right? So it's really the extent to what we were able to do. And to be honest, coaches, right? They often do tactical situations on a whiteboard with different players as nodes, right? So it's not so uncommon in terms of like what a coach would actually look at, right?
Got it. Makes sense.
Yeah. So this is the takeaway from the first part. The second part, which I think is also quite exciting. Sorry, Ivan, you have a question?
Hi, yeah. I was just wondering if you could briefly explain how you explained how there are some predictive tasks on the model, but how do you use that model to generate?
Yeah. I'll say it very quickly because I know Aleksa doesn't have a lot of time, but basically it's a variational autoencoder. So it's not even, we're not predicting adjustments, we're reconstructing. So you have the original situation and the shot event, 0-1, and the VAE reconstructs the players, right? Then what we do at test time is we show it an actual situation, but we flip the shot flag and we ask what the VAE will reconstruct based on that, right? So the model was never instructed to make tactical advantages. It's trained to minimize mean squared error. And therefore, when it does make suggestions, they will be small. And this is great for us because we want realistic suggestions, right? Yeah. Okay. So one thing that I'm quite excited about also about the system is that it can be used for retrieval. So we are solving all these different predictive tasks, like who receives the ball, will there be a corner, will there be a shot event and stuff like that. All of these things, when you train with backprop, result in good high-dimensional player representations being computed. And you might imagine similar corners, hopefully clustering together in that high-dimensional space, right? Why is this useful? Because a video analyst, when he has to watch, prepare a team for a new opponent, he has to watch hundreds and hundreds of corners usually to prepare themselves for the tactics. And often it's really helpful if you have a system that will tell you, look, these are the top 10 corners you should be looking at, right? So retrieval is really important for a video analyst's job. So we wanted to see, this is first just a simple study of the T-SNE space inside TacticAI, and just some simple observations we made, obviously without a lot of football knowledge. Two corners that end up really close together. As you can see, we highlighted it, tend to have many similar patterns happening, and they're both, in this case, outswinging corners. So this is a pretty good sign already, that the system learns to put together corners that have kind of structural similarities. And two corners that are far away, they end up being really different. So here you have one which is an in swing and one which is an out swing corner, and those are very different tactically to prepare for. So this is a good sign, and we wanted to do like a human case study to kind of hammer this point home that these representations are useful. So we needed a baseline. We took just one baseline. It's not the best baseline in the world, but it's just a simple measure of what a team might do with simple data analysis on the corner data they have, right? So let's just mine the closest corner using raw coordinate similarity, right? So like find me a corner where the players are roughly in the same place as much as possible, right? If you retrieve a corner based on this metric, humans only find this useful about 33% of the time. So we showed them a pair of corners and asked, do you think these two are usefully similar to each other in a way that's helpful for your job, right? Only about 33% of the time was the raw feature similarity a good measure for mining a similar corner. Then you compare that against TacticAI embeddings as a retrieval system, and you actually get that the recall almost doubles. So from 33 to 63%. So humans generally much preferred what these high-dimensional embedding spaces told us versus just what we can get from raw coordinates. So clearly, it's learning something about the football game dynamics that can be really useful for a video analyst's job. And one thing that's also very important is that there is a high level of inter-rater agreement. So it's not just that on average the recall doubled. It's also that on every situation where it improved, humans tend to agree with very high p-value, right? So they have a very, very like related way of rating these things. So it's not just a case of one person is enthusiastic about AI, the other one is not. They're actually agreeing a lot on these things. So what to take away from this? Experts prefer retrievals that come from TacticAI compared to ones coming from just raw features. Obviously, we only tried one heuristic, but I think it's a good indicator of how far you can get with just raw coordinates. And experts have a high degree of agreement over these ratings. So this is a good place to start. Lastly, the most exciting part, right? The generative model, as we just described. So we have shown our human raters a pair of situations where the attacking team was in the same place, and we changed the defensive team positions. And they have to tell, we don't tell them which one is original, which one is AI. They have to say, does TacticAI improve the situation or not? And we assign ratings based on what they say. Either it improves, makes it worse, or no significant difference. So the average rating we received across all 50 corners, we showed them in this particular case study, was 0.7, which I think is a pretty damn good score considering the scale goes from -1 to 1, right? So it's a pretty good rating. But one that might be easier to communicate externally is you can look at every individual corner, average the scores the humans gave, and if it's a positive score, so if it's by majority vote, a good situation for the defending team, then you say that TacticAI offered a good suggestion for this one. And that happened 90% of the time. So for 90% of the corners that we tried, the average majority vote was that TacticAI's recommendation was good. Yes, Aleksa?
This is impressive as well. I'm just wondering, do you have any distribution to see how many -1s you actually have? Like, I'm just curious to see whether it's being compensated by the +1s or you have a lot of no significant difference scores as well.
No, a lot of it is plus and -1. Very rarely will a coach give a 0. And that's usually when they think it's already like tactically optimized, so there's not much more to do, right? And maybe this answers the second part of your question, but the inter-rater agreement is again high. So this is not the case of some person really likes the AI recommendations that drives the average up, but actually on individual examples, we have a high p-value for inter-rater agreements. So this is also good. So what does this mean? 90% of the time, at least over the 50 corners we showed them, experts prefer TacticAI suggestions over existing tactics, and there's a high degree of agreement over this. It's not just a case of one outlier who like really likes it, that compensates for others that don't. Okay. And I feel like it's also useful to just show you some of TacticAI's greatest hits. You can see these in the paper and our blog post as well. I should note the velocities of the attacking team are not completely normalized left and right. So keep in mind, these are actually exactly the same, just the normalization factor is a bit different. So look more at orientation than the magnitude. So this is one specific example where TacticAI actually corrected almost all the players properly. So the yellow circled players are the ones where the coaches thought this was a good suggestion, right? And you can see the goalkeeper is a bit deeper, which is a better position for the goalkeeper to be. You have some of these defensive people in the middle that are trying to block the attacker or just moving in a completely weird direction altogether. And TacticAI notices this and learns to correct their course. And sometimes if a block isn't going to work, it's better to track. So it suggests the defender to track the attacker. So this is one situation. Yes, Aleksa?
How do teams in practice and coaches and players use this information to improve their game? Because a lot of times you had, like, for example, how do I tweak the velocities and positions of the players so as to reduce the chance of somebody like shooting the ball towards the goal? Like, how do you actually integrate this into day-to-day? Like, just curious about those practicalities of the
we got direct feedback from Liverpool experts on how this might be useful to them. Of course, the idea is not to coach the player, go back in time to this exact corner and do it like this. No.
And move 20 centimeters.
Yes, exactly.
To the left.
It's more about detecting like higher order, patterns in what tactically needs to be done better or differently. And then basically, you want the player, it's more to detect if a player is asleep on the wheel, because these are really minor tactical adjustments. This won't teach you new tactics, right? It will more show you who is not doing their job right. If it's someone you're playing against, then you can train your own team to attack that player, because that player is going to be a weak link. If your player is a weak link, then you can coach them to prepare better for those specific tactical setups, right? Those are the kinds of things that already, I think, can make a big difference in coaching. And at least there was a lot of enthusiasm from our collaborators that when we talked to them about this. Let me show you a few more greatest hits, some of them more localized. The first one was cherry-picked because almost the entire defensive team was in a bad place. Maybe this was a weaker club in the Premier League, I don't know. But here you can see some other situations where, again, you have defensive players sometimes moving in completely weird directions away from where the ball is being kicked and stuff like that. So TacticAI makes salient recommendations to actually be positioned better, track your attacker better, don't be confused, right? And sometimes, like in this situation, you can see a few very salient players in the middle. So it detects that, like, in the box is really the players that are not doing a job right. They're just running away from where the attacker is going, and it's not helpful. You might want them to move a bit more, tracking the attacker, right? And similarly here, this was one of the situations where almost all the players were deemed to be in a good place to begin with, and there were like only a handful of players, like 3 players, for which you really want to do something better. But TacticAI found those players and immediately surfaced this information to the coach. By the way, I'm not saying that a coach will not be able to predict these kinds of things better than TacticAI and provide a better tactic. It's more like it's hard to track these things across 22 players, and this system gives you a suggestion immediately in like seconds. So it can help you kind of iterate more faster and do the more creative part of the job more sooner, right? So in conclusion, we're basically exactly at time, so I'm going to just run you through some of the main findings we had. We studied a dynamic set of problems around inferring corner kick dynamics, and powered by GNNs and GDL, we were able to have increased data efficiency, even though there's not so much gold standard data of corners played every single time. And we have a model that's both predictive, so it can tell you things that happened about the situation, but also generative, so it can predict what you might want to do differently to get better, realistic, quantifiable adjustments of player positions. And in a blind case study with human experts from Liverpool, these adjustments are deemed significantly useful. And also it's a domain like corner kicks where that usefulness might transfer into actual decisions. In short, I believe and I hope I've convinced you that we now have an AI assistant for football tactics on our hands. I'd love to debate that more if you have additional thoughts or questions now or at Discord. That was my last slide. Thank you very much for listening. Thank you, Aleksa, for welcoming me to the server one more time. I hope that there'll be more opportunities in the future. And yeah, just happy to continue the conversation. I hope you enjoyed it.
Thanks, Petar. Thanks a lot. Yeah, definitely. Like every new exciting paper you publish, I'll get you over here to give a talk. So that's kind of given. We had a lot of questions in the chat. Let me see. Maybe we can cherry pick a couple of them, given the time. So let me see. Or Petar, if you have any particular one you've seen already and you want to address it, we can do it that way as well.
It flew by really fast, so I don't have any picks. Aleksa, you can decide whatever you think is best.
Okay, maybe a bit more generally, and then you can like address some of the more specific ones in the Discord. What's algorithmically? What was the hardest part? The biggest challenge of this whole project?
So
or not necessarily algorithmically, data-wise, or whatever, technically.
Right. I mean, I think that it's quite interesting to think about it, because you would expect a kind of a deep applied project like this with a team that hasn't used deep learning technologies before to be full of, like, these kinds of deployment issues. But actually, I didn't really experience this that much, because we were really working with people who were enthusiastic about this stuff and understood it from a physics perspective as well. Like, generally speaking, I think the biggest challenge was how to put together this case study in a way that we would get useful answers without wasting too much of the precious time that these coaches have, right? Because obviously we cannot hold them for a month. We need those answers in a shorter period of time, because they have a full-time job, which is very important to attend to. But if we found in the early pivots of the case study that if we showed them a particular situation or a particular question in a bad way, we would end up spending 10 minutes on one corner, and we needed to go through 300. So it took a lot of revision and refinement before we arrived at like a question that would give us an immediate like yes or no answer, and like a immediate pinpointing of which players were the most important for the adjustments and stuff like that. But it took a few iterations before we got there. And I've never done a human case study before, so I was kind of learning the ropes as I went. Luckily, a lot of my colleagues at GDM have expertise with these kinds of things. So I was well supported, had a good support network, and the folks at Liverpool were very patient, sometimes very enthusiastic to overanalyze every single situation with us. But like, I think that was the main challenge for me, just the human element. How do we design this in a way that we're kind of having an unbiased study that will lead to scientifically useful results while also not wasting anybody's time? That was like the key problem, I think.
Nice. I mean, I think somebody had a question about the data. Was the data mostly or solely coming from the Liverpool Football Club, or
yeah? So
can it be extrapolated to other teams? Can it be useful more generally?
Oh, no, this data spans the entire Premier League. So all clubs in the Premier League have access to all of this data concerning all matches. Liverpool obviously will have access to some special features they're extracting, or some special other leagues they have access to, obviously. We deliberately did not use that data, partly for proprietary reasons, partly because we wanted to see how much you can get with just the rudimentary features. But yeah, these features concern all the clubs in the Premier League, all the matches in the Premier League over the last 3 or 4 seasons, I believe. You have details in the paper.
Nice. And one more on my side is, somebody mentioned synthetic data in the beginning of the talk. Have you been considering that a bit more? How would you go about doing that? Maybe collaboration with Nordus or something. I'm joking, but like I see self-play and something like that could be a potentially interesting source of generating new bits of information and then training the GNNs even further. Like, how do you think about the whole self-play aspect?
Yeah, for sure. I mean, I think that it can be quite impactful. The thing that, the main point here is that I hope you've seen how even like the ground truth labels, the humans cannot tell these things very accurately, right? So I have a feeling that, you get lots of synthetic data. You're not necessarily going to get better at predicting the variations of the game. But you might end up overfitting to whatever the game engine tells you, right? So it's they've gotten really realistic, the game engines, in recent times, but there are obviously subtle differences, and depending on whether you play, well, they're not called FIFA or PES anymore. They both changed their names recently, right? But depending on which game you're playing, you'll get different dynamics and different controls and stuff like that. So like, this variability is not the confounder we wanted to consider in our particular paper. But that being said, like, clearly having access to that kind of data can help you, pre-train a foundation model, for example, because you'll have access to a lot more dynamical stuff. It will be tied to one particular simulator, so you have to be careful about that. And but also it can be a bi-directional thing, right? Like, you could imagine in the future a game studio might really want to make advantage of a predictor like this to basically improve how their game runs and how the teams set themselves up in situations in game. Because even though these games are quite far advanced, you would imagine there are still some situations where you get upset at the game engine for making the AI do something that actually humans would never do in real life, or something like that.
when you're talking about like overfitting to a game engine, what I had in mind is this paper from OpenAI back in 2019, solving Rubik's Cube with robot hand. And the idea basically was to just vary everything from gravity to friction, et cetera, et cetera. So from that standpoint, and then you would just give the actual parameters during the inference time to specify to the model, hey, this is the type of environment you're dealing with. And then I guess you would have less of such problems of overfitting to peculiarities of a particular game engine. That was my idea, at least.
Yeah, I mean, it's a great idea. I'll just say that Rubik's Cube has way less multi-agent factors compared to football, right? But I do agree that you could try to do this. I'm just a bit skeptical over how easy it will be, but someone should try it if they have access to that data.
Just stack more layers. Awesome, Petar. Thanks a lot for joining. This was amazing.
Yeah. Can I just quickly answer one more thing? Because I saw there were people asking, if they wanted to build a similar thing and so on. I'll just emphasize that the core part of our architecture is open sourced, so you can find it on Google DeepMind's GitHub, and there's a pointer in the paper to where you might find it. Just find the D2 equivariant GAT-V2, and that's the core, that's the heart model that we use inside TacticAI. We cannot release encoders, decoders, and data processing because all of that comes from Liverpool and it's proprietary data that they pre-processed. So we don't want to reveal anything about that. But you have the central part of the model. So really take your favorite sport, find some open data. For some sports, there is open data to be found. I think for basketball, there is some lying around. And, build your own encoder and decoder and train your own model. Our models are in JAX, by the way, which I hope will not be a limitation. I personally really love playing with JAX. But yeah, like if you want to do something, the heart of the model is open sourced.